Hi everyone, I'm Caden again. This is the talk I actually prepared for this. So this is about this is my master's thesis work, and it's been a huge collaboration with a bunch of folks at Cornell, Brooklyn College, the USGS, NOAA, EPA, and so I just want to thank everyone for all of their help and mentorship. And I'm sure there's double that I have left off of the slide. Um, so the title of the talk is Availability of Dark Daytime Refuge May Limit Mysid Abundance in the Great Lakes. This is recently accepted in the Canadian Journal of Fisheries and Aquatic Science. And so we'll get to it. What are mysid shrimp and why are they important? We'll get into that first. We'll quickly go into the status of mysis in the Great Lakes based on net tows. We'll go into the establishment, walking through how we thought through the dark habitat or dark refuge hypothesis. Look into how we tested that hypothesis in 2021 using hydroacoustic and net sampling, and then some future spin-off directions of this work. So what are mysis? Mysis diluviana. I might say mysid in this talk a lot as well. The species of interest is Mysis diluviana. They are a 325 millimeter long crustacean. They're found in many deep North American lakes. They're very large relative to other zooplankton in a lot of these lakes. Here's an example of some plankton from a tow in Lake Ontario in July of 2023. We see a mysis, adult mysis in the middle, a juvenile mysis here on the right, and then a bunch of smaller copepods of some sort, just to show the relative size scale of these animals. Mysis are extremely important as predators of zooplankton, but also as prey items for fish. They are omnivorous. They feed on zooplankton, algae, as well as detritus in the lake bottom. Most fish in the Great Lakes will feed on, especially in the offshore Great Lakes, will feed on mysis at some point in their life cycle. And mysis exhibit a partial diel vertical migration, as seen in some of those echograms earlier, and there'll be plenty of other examples in this talk as well. It's hypothesized that this diel vertical migration is evolved due to a light predation mechanism or a predator avoidance mechanism, as they are visually under a lot of predation pressure. Just pulling out show how central they are to the Lake Michigan and other lake food webs. They're right at this central location, funneling energy up from the lower trophic level up to the fish. There's also been a relative increase in importance of mysis as this benthic amphipod diparia has decreased. So here's an echogram. You see actually the exact same one in the prior talk, but we see the trends of the patterns of migration where we have mysis shallow up in the water column above 50 meters or so in Lake Superior. At night, as soon as the sun rises, they migrate down, in this case to about 200 or so meters is this depth. The lake bottom is deeper than 250. We see some potentially interacting with the lake bottom and some forming a strong pelagic daytime layer here. We see all of these fish targets about 50 meters above the mysis. These are what we believe are kai, with individual kai sort of making foraging forays down into the mysid layer during the day. So what are the status of mysis in the Great Lakes? They were recently added as a sub-indicator into the State of the Great Lakes report. This figure is from that report. In recent years, there has been a dramatic decline in the density of mysis in both Lakes Michigan and Lake Huron. Lake Michigan is here in blue. Since about 2005, there has been a steady decline in offshore mysid densities. These are from net tows. And in green, Lake Huron, there's been a decline from 2000 to 2005, and then a steady low numbers in Lake Huron since 2005. Some recent work by Toby Holda et al. Has linked that these trends of mysis abundance with the declining productivity and food availability for mysis in the lakes. However, one question we had were that densities in Lake Ontario, which are in purplish here on top, as well as Lake Superior, which is in yellow, have remained relatively high and relatively stable, despite Superior and Ontario being on relatively opposite ends of what we think of the productivity spectrum of the lakes. So another factor going on in the lakes right now is water clarity is increasing. There's been a ton of work documenting this. This has been due to decreased nutrient loads as well as the invasion of dry-scented mussels. And so this led to our development of this dark refuge hypothesis for mysis. So typically when we're sampling them at night when the mysis are up in the water column. We use net tows and we do a pelagic net tow up to the water column and we count the number of mysis. We also do this under red light as it avoids reaction from the mysis. They can't sense the red light deeper in the water column. However, during the daytime, we know that mysis descend to a depth where we presume it's dark enough for them to avoid predation. And we're going to call that dark habitat, where light reaches darkness to provide them from refuge from visual predation. We know from previous work in experimental experiments at the Cornell Biological Field Station that alewife feeding on mysis significantly decreases with decreasing light intensity and is significantly lower in levels of, this is an alelux, which is a little confusing, but in low levels of light. It equates to about 10 to the minus 5 lux. So, say in a previous light regime in 1996, for example, light would penetrate down to a certain depth, say in this case 100 meters. That would result in this section of the lake being dark and a low pressure of predation, and then some other section of the lake being a high predation area. If water clarity increases, light will penetrate further down into the water column, and we will see less area of the lake that maintains this dark, low predation pressure habitat, and more area that's high pressure. So to sort of build this to look at this with data, we use offshore sites collected from the Lake Guardian. We used Secchi depth measurements sampled in spring on the left and summer on the right. We used a pretty rough estimate of lake-specific mean Secchi depth for each season and each year. There definitely would be a lot more, there could be a lot more looking into spatial patterns within the lakes, but we used a pretty rough estimate for each lake. And we do see a significant increase in Secchi depth in blue in Lake Michigan in spring and summer, as well as Huron in green, spring and summer, and then Lake Ontario in pink. We'd see an increase in spring, but no real change in summer. There's been very little change in Secchi depth in this data in Lake Erie, as well as in Lake Superior. So then we can calculate or estimate a dark depth, so the depth of where mysis would perceive darkness. So we calculated this using the Beer-Lambert law. We calculated the depth of darkness using modeled surface light intensity from the a astronomical light model. We used the K-par value that is from this relationship from Annie Schofield's deep chlorophyll layer paper, correlating Secchi depth with light attenuation coefficients from the water column profiles. And then we know the intensity of dark from the previous experiments. So we can then calculate what the depth of what mysis would perceive as darkness is. And we see that similar trend where no real change in Lake Erie or Lake Superior, but a increase in that depth, so it gets deeper in Lake Michigan, Huron, and Ontario in spring, and again, no real change in Ontario in summer. So now that we can estimate what the depth that mysis would perceive darkness as, we can then calculate the percentage of lake area that would meet this criteria, because we know roughly the bathymetry of the Great Lakes. So we use the NOAA bathymetry data sets to calculate the percentage of lake area that would meet that criteria over time. And we see there has been as well a decrease of that percentage of lake area in Lake Michigan, Huron, Ontario, and no change in Superior. And I've left off Erie on this as there's been little change in Erie. Looking at this geographically in the lakes, I think it's pretty striking. We have blue, of course, the overall lake area, In gray, we have what would previously have qualified as dark habitat in the lakes. And then in black, we have what is currently, or back until 2021, classified as dark habitat in the lakes. Specifically, you can see in Lake Michigan, there's been a complete loss of dark habitat in the southern basin and a restriction to this really deep northern Chippewa basin. In Lake Huron, there previously was significant dark habitat, even in Georgian Bay, but now it's restricted to very small areas of the main basin. There's a slight change in the spring in Lake Ontario, shifting more towards this deeper area of the lake, and no significant change in Superior. In the summer, we see a similar pattern without any change in Ontario. However, we do see a similar pattern in Michigan and Huron, just less severe. So to look at the actual distribution of mysis in the lakes in 1 year to test this hypothesis, see if this is actually driving mysis populations, we used a combination of net tows as well as a hydroacoustic survey in the summer of 2021. The net tows were a combination of EPA, NOAA, and USGS net tows from the 2021 Lake Michigan CSMI year. These were a 1 meter diameter net with a 500 to 250 micron mesh. The hydroacoustic survey was also conducted during nighttime, used a 120 kilohertz transducer, and it was mounted on one of the sail drones that we had previously been talking about. So in the summer of 2021, this shows our sampling effort. The orange is the nighttime sail drone sampling track that is suitable for mysis assessment. We know from previous net tows that mysis aren't found in any densities really shallower than 40 meters bathymetric depth in the Great Lakes currently. And so if you see some disconnected points like right here, it's because it gets a little shallower. The diamonds correlate to the locations of the net tows. I'm going to go very quickly over this because a lot of people have described the sail drones, but they are large, 7 meter long, 7 meters-ish tall, self-propelled drones, wind-powered and solar-powered, and then you guide them remotely through the lakes. We are primarily looking at the echo sounder data collected from the keel. So I showed this previously, but we get this kind of data from the sail drone. I'm going to go through a couple other examples. Lake Superior, we see a very similar pattern in 2022, as well as in 2024. A couple more in 2022. I'm going to go very quick. All right. So now in Lake Michigan, we weren't able to look at their migration through the entire daily cycle. We had a slightly higher signal to noise or lower signal to noise ratio where we couldn't see mysis deeper than, say, 70-ish meters or so. But we can see mysis when they are up at night in the water column. Here are 3 examples from Lake Michigan where we have one zone with very little mysis, a moderate typical mysis layer, and then a very dense mysis layer here in the northern basin. So what we are doing is we take this total amount of backscatter in this Mysid layer, and then we divide it by the Mysid backscattering cross-section to get an estimate of Mysid density in this layer. You can also see above the Mysid layer a combination of fish targets that are masked out, these black dots, and other zooplankton. So to estimate the density of mysis, you need to know the backscattering cross-section of mysis, which is a very complicated relationship of the target size, the frequency you use, the shape of the target, how it's oriented in the water column, as well as the physical properties of its density and the sound speed difference. We used the distribution of lengths of mysis caught in Lake Michigan and Lake Huron in that summer to weight the target size, length parameter of this, while keeping all the other parameters constant based off of some previous work to estimate a lake-specific backscattering cross-section for a mysid. And we did see slightly larger mysis in Lake Huron than in Lake Michigan. It could be due to sampling Huron a week or 2 later. So then to measure mysis without including fish backscatter, if you include a single fish in your estimates, it's going to say that one fish is 1,000 mysis based on the amount of sound returning. We have to exclude them using a series of steps in our processing where we take individual values that are greater than, say, minus 60 dB, and we mask those out from our analysis. So now looking at the results of our survey in 2021, we do see that the highest densities of mysis, the size correlate to the size of the circles here, are in the northern basin of Lake Michigan in the hydroacoustic survey. The black lines are the sampling track for that night. We see a similar trend in the net tow data where the higher densities are in the northern basin with scattered densities throughout the lake. Looking at this at the scale of bathymetric depth bin, each data point is now a 200-meter section of transect of sail drone track. We see a pretty consistent pattern between both the acoustic data and the net data, where we have an increase in density with bathymetric depth. However, there is a slight difference in the absolute abundance estimates of mysis between net data and acoustic data. This could be due to using a single size distribution rather than changing that based on where you are in the lake. However, we also know that acoustics in general scales better to biomass than total numeric density. I do want to point out that the sail drone data really allowed us to sample areas of the lake that we were not able to get to, even with the combined multiple agency net tow survey, where we're not able to get any samples in Huron deeper than 160 and nothing deeper than 200 meters in Lake Michigan. We were able to effectively sample that with the sail drones. So some quick takeaways. Hydroacoustics can be used in combination with net tows to increase the overall spatial coverage of surveys and reach areas that you previously would not sample. However, you still need the physical net tow data in order to ground truth that with the size distribution, sex ratios, fecundity information, etc. Uncrewed surface vessels specifically also allow you to increase that acoustic coverage even more than you would be able to with using a crewed vessel. And also I want to point out that a combined USV and net tow survey can be used to inform ecological understanding and develop new hypotheses. So to be continued, a lot of this is going to be spinning off into my future PhD work. We just got a project funded through the Great Lakes Fishery Commission to evaluate mysid abundance in Lake Michigan using 2 decades of previously collected fisheries acoustic data to see if we see a similar pattern of constricting distribution of mysis in Lake Michigan. And we have a similar project in review for Lake Ontario. We're developing a standard operating procedure for mysid acoustics. We have a lot of folks in this room that are collecting hydroacoustic data that I think we can leverage to get more information about a key pelagic invertebrate. And then as well, some of the surveys from Lake Superior in 2022 and 2024 we're working on to look at the vertical distribution of fish and mysis as well as the horizontal distribution of them through the lake in a 1-year survey. And with that, I will take any questions.